Work, energy, and power. These three little words, they pretty much run our entire universe. But what do they actually mean? Well, in physics, their definitions are super precise, all connected, and honestly a little bit surprising.
Okay, so let's start with something I'm sure we've all felt. You spend the entire day head buried in books preparing for a huge exam. By the end of it, you're just completely drained, right? Mentally exhausted. You feel like you've done a ton of hard work.
But what if I told you that in the world of physics, all that studying, all that mental effort added up to, well, zero work? How is that even possible? That's the cool paradox we're going to figure out today.
So here's our game plan. We'll start with this hard work paradox. Then we'll nail down what scientific work really is. From there, we'll see how that connects to energy, check out its different forms, uncover the amazing law of conservation, and wrap it all up with power, which is all about how fast you get things done.
All right, let's jump right into this paradox. You see, there's this massive difference between what we feel like is work in our daily lives and what science actually calls work. Just think about it for a second. Someone like Kamali studying for hours, or imagine trying to push a giant boulder that just won't budge, or even just holding a heavy bag on your head, standing perfectly still. All of these things are exhausting, right? They burn your body's energy. But here's the kicker. In physics, because the thing you're putting effort into isn't moving, you're doing absolutely zero work on it.
So if all of that effort isn't considered work, then what is? Well, the scientific definition is actually pretty simple, and it all boils down to just two crucial ingredients.
This right here is the main idea. For work to happen, in a scientific sense, two things are absolutely essential. You need a force, and that force has to cause some movement, what we call displacement. Let's break that down step by step. First, there has to be a force, some kind of push or a pull. And second, that force has to actually make the object move some distance. If one of these is missing, say you're pushing but nothing's moving, then no work is done. It's really that simple.
And of course, there's a neat little formula for this. Work equals force multiplied by the displacement. So the harder you push, or the farther you move something, the more work you end up doing. And it gets even cooler than that. Let's say you push a box and it slides forward. Since your push and the movement are in the same direction, you're doing positive work. But what about friction? Friction pushes back, against the movement. So that's what we call negative work.
Okay, let's look at a real-world example. A porter lifts a 15-kilogram bag about 1.5 meters off the ground. By applying that force over that distance, he does 225 joules of work. And that J for joules, it's like the official unit we use to measure both work and energy. It's how we keep score. So we know that doing work means you have to apply a force that makes something move. But what do you need to even apply that force in the first place? Well, that brings us to our next big idea, energy. I love this definition because it's so simple and direct. Energy is just the ability to do work. If an object has energy, it has the potential to make things happen, to cause movement. It's basically the fuel that makes work possible. And wow, energy is everywhere, and it comes in so many different forms. We've got chemical energy in our food, electrical energy in our gadgets, heat and light from the sun. But for today, we're going to zoom in on the two main types of what's called mechanical energy. So let's break down this mechanical energy. It splits really nicely into two basic types. There's the energy something has because it's moving, and then there's the energy it has stored up just because of where it is.
We call these kinetic energy and potential energy. Kinetic is the energy of motion, the energy of doing, and potential is the energy that's stored up, just waiting for its moment to be released.
A car driving down the road is the perfect example of kinetic energy. Now look at that formula. The energy depends on the car's mass, sure, but it depends way more on its speed. See how the velocity is squared? That means if you double the car's speed, you don't just get double the energy, you get 4 times the energy. That's huge. And potential energy? Think of it as energy just waiting in the wings. When you pull back the string on a bow, you're doing work and loading it up with potential energy. The second you let go, bam! All that stored potential energy instantly transforms into the kinetic energy of the arrow flying through the air. And one type we deal with every single day is gravitational potential energy. Anytime you lift a book off a table, you're working against gravity. That work gets stored in the book as potential energy. And the higher you lift it, the more potential energy it gains. Okay, so what happens to all this energy as it changes from one form to another? Does it ever just vanish? Physics has a really powerful and beautiful answer for that, and it's called the law of conservation of energy. This is honestly one of the most important rules in all of science. It means you can't just make energy out of thin air, and you can't make it disappear either. The total amount of energy in the universe is constant. It just changes its dress, going from one form to another. Let's picture this. You're holding a ball high up in the air. At the very top, before you let go, it's packed with potential energy. Then, as it falls, that potential energy starts turning into kinetic energy, which is why it gets faster and faster. Right before it hits the ground, it's almost all kinetic energy. But here's the amazing part. At any point during its fall, if you add up its potential and kinetic energy, the total is always the exact same. We've talked about work, we've talked about energy, but there's one last piece of this puzzle. It's not just about whether you can do work, it's also about how fast you can do it. And that, my friends, is where power comes in. Power is simply how quickly you get work done, or how fast you transfer energy. If you do the same amount of work but you do it in half the time, you've used double the power. This example makes it super clear. Look, both girl A and girl B do the exact same amount of work, 3,200 joules. But girl A does it in just 20 seconds, while girl B takes 50 seconds. Since girl A did the work faster, she was more powerful. She generated 160 watts, which is our unit for power, compared to just 64 watts for girl B. And that brings us to one last kind of mind-bending question to think about. We've seen how energy is always changing, potential to kinetic, chemical to mechanical. But imagine if it couldn't. What if nature just didn't allow for this transformation of energy? You know, life as we know it, everything we see and do just wouldn't be possible. It's this beautiful, constant dance between work, energy, and power that really makes the universe tick. Thanks so much for exploring this with me today.